Hello and welcome. In this webinar, which is a companion presentation in a two-part series, we're going to discuss a wide range of products that are created from dairy manures as well as various other manures following different types of nutrient recovery approaches. If you're interested in reading the publication from which we developed this webinar, that can be accessed online or downloaded as a PDF at the URL listed on the screen. My name is Stacey, and I'm a postdoctoral research associate in the Center for Sustaining Agriculture and Natural Resources, and I conduct research primarily focused on the reuse of organically based products in different agricultural systems. Because dairy manure is an organic byproduct, I have an interest in these technologies, products that result from their use, and the potential effects in different cropping systems. While the publication generally focuses on dairy manure feedstock and the materials produced from the refinement of that manure, for this presentation, we're going to broaden our scope a bit and include all types of animal manure, whether it be from dairy cattle, beef cattle, pigs, and so on and so forth. No matter the type of animal system we're considering, those managing each of those systems has to deal with animal waste, or manure. If we consider just three animal categories, dairy cattle, pig, and chicken, we can gain an understanding of manure production by considering each one individually. On average, dairy cattle produce about 54 kilograms of manure per day, pigs 6.4 kilograms of manure per day, and chickens 0.2 kilograms of manure per day. If we combine just these three groups, we get annual manure production of about 55 billion tons. That's a lot of waste, but maybe instead of considering manure to be a waste, we can think of it as a resource. But you may ask yourself, why would we consider manure a resource? Simply stated, manure is rich in plant nutrients like nitrogen and phosphorus, organic matter, really what we're considering there is the carbon, and other plant micro and macronutrients that we won't get too deep into here. Manure then, and the refined downstream products could be used to supplement crop needs. What becomes difficult in this situation is applying the correct amount of manure to meet crop needs without exceeding the rate at which the application degrades the surrounding environment. That can be a very difficult proposition when dealing with raw manure because of its liquid form. Not only is it costly to transport long distances, but there is a greater chance for it to move off-site from the target location. Therefore, to decrease the likelihood of over-application while providing a local source of nutrients, many technologies have been developed that alter raw manure both physically and chemically. If you joined us for the companion webinar in this series, then you may recognize the mention of these technologies. We won't go into each of the actual technologies here. Rather, we're going to focus on what results from those technologies, the products of those processes. To be clear, some of these technologies and the resulting products are relatively new, but we'll still review them and provide as much information as has been gathered to date. Again, if you're interested in the specific studies and data, those can also be found at the URL listed here under the title Nutrient Recovery, Products from Dairy Manure to Improve Soil Fertility. Let me list these off to give you a preview of what we'll be discussing. First, we'll look at the solids that result from anaerobically digested and screened manure. In contrast to relatively new technologies, this is not a new product. This has been around for many years. In addition, we'll talk about separated solids, phosphorus-rich fine solids, struvite, ammonium sulfate, and finally, we'll touch on a few products which are still in the development stage but have the potential to make it to market. In some cases, in fact, these other products are being produced at commercial scale on at least a few dairies in the northwestern United States. In the fact sheet, We provide background information on raw manure and anaerobically digested manure as points of comparison, given that these are more widely available. So, raw manure aside, anaerobically digested manure results from anaerobic digestion. On the slide, you'll see here a very simple diagram illustrating that process. Raw manure is used as a feedstock to anaerobic digestion, and after biological transformations occur, what results is a gas, a solid, and a liquid. In comparison to raw manure, after manure has been anaerobically digested, concentrations of ammonia N and ortho P increase somewhere between 20 and 40%. That orthophosphorus that I just spoke of is like a single unit of inorganic phosphorus unbound to organic matter. For N, microbial action converts the organic N into the inorganic ammonia N form. Because there is a higher concentration of ammonia N in the AD manure as compared to the non-AD manure, there is a potential for greater N loss due to volatilization. Volatilization is simply a chemical transformation where the ammonium is converted to the gaseous state and therefore lost. Conversely, because a portion of the solids are removed during the process, AD manure, under circumstances where there is little to no volatilization, may provide more soluble N in comparison to non-AD manure. This soluble N may move through the soil quicker, making it more plant available. When thinking about this product, we want to think about its effect on soil nutrient availability and therefore crop yield. If we choose to apply this to our fields, this product will provide N, P, and K, that is, nitrogen, phosphorus, and potassium. Some research has shown that when applied to grasses harvested for silage at equal rates of N, AD manure provides similar amounts of N in comparisons with non-AD manure. A few moments ago, I mentioned the fact that AD treatment reduces the total amount of solids in the raw manure. Interestingly, the solids that are left over can themselves be considered a product, and those are known as separated solids. If we return to our earlier diagram of AD, the separated solids are these fibrous organic materials that can be removed by mechanical or gravitational methods. Typically, nutrient concentrations in these materials are lower, and therefore they are often used as bedding material. With that said, some greenhouse studies have shown that when this material is used as a substrate in potting studies, it provides benefits equal to those observed in pots amended with peat moss. Important to note that in this particular study, the post-anaerobically digested products were pH adjusted. At the time of our review, very little, if any, work had incorporated this material into the soil in field settings, so clearly more work needs to be done to better assess the potential use of this material as a soil amendment. In our manure product narrative, we've just removed these large fibrous materials. But in this effluent discharge, the black pipe here, there are still, albeit very small, suspended solids. There are only two ways to get at these. One, using a centrifuge, or two, with dissolved air flotation, also known as DAF. In either case, what results is a phosphorus-rich fine solid, which is recovered in a wet form and then de-watered to make a suitable amendment product. You may then ask yourself, what is this product like? Well, one, it's very fine, as the name suggests, and clay-like, and two, it's likely to have a nutrient content of 2-3-1, that is, 2 parts nitrogen to 3 parts phosphorus to 1 part potassium, though that can vary depending on the specific technology used and the composition of the manure input. As far as its nutrient availability, This product is organic, like many of these materials, which means that its release to the plant is heavily mediated by microorganisms, which is a shorthand way of saying that it's heavily influenced by soil temperature. When the microorganisms, depicted down here on the slide, are finished munching, what results is a P, or phosphorus, that the plant can use. When researchers tested this type of material in the field, between 50 and 60% of the total phosphorus applied was available in 3 months. Additionally, when this material and a standard phosphorus fertilizer were compared in a potato cropping system, like the one shown here, researchers observed similar tuber yield and vine biomass and increasing P uptake with the standard. The second observation makes sense if this product, which we've mentioned earlier, is dependent upon soil microorganisms and temperature. Now we're going to switch gears just a bit relative to form and discuss a crystalline product that is also derived from the effluent water discharge. Each one of the crystals depicted here is known as struvite. Clearly this is a magnified view of the product, but if we zoom out, struvite would resemble and has the consistency of sand. In addition, it has a low moisture content, which makes it easy to transport. Sometimes these technologies are also used at wastewater treatment plants to reduce or remove additional phosphorus. Compared to some of our other products, struvite is somewhat unique. Its chemical form is illustrated here. We have the usual suspects, forms of both nitrogen and phosphorus, but with this product we also get a bit of magnesium. This is something to be aware of. As far as the fertilizer value and nutrient availability goes, this product is labeled as a 6-29-0 plus 16 magnesium, and similar to the phosphorus-rich fine solids, about 50 to 60% of the P applied is available in 3 months, and that research was conducted in the Columbia Basin. Unfortunately, to date and locally, there is little information on the availability of magnesium, but other researchers in different environments have observed similar rates of magnesium uptake following struvite amendment and in comparisons with a conventional source. Fortunately, when it comes to plant growth and yield studies, we have a much better picture of struvite's activity. In wheat, corn, and alfalfa, yield and phosphorus uptake were generally equivalent in comparisons between a conventional monoammonium phosphate and struvite, but the magnitude of these effects seems to be dependent upon soil pH. The greatest benefit and likely availability of phosphorus are observed in lower pH soils. Additionally, other researchers observed similar responses in potato, where yield, phosphorus concentration, and tuber size were generally equivalent between a monoammonium phosphate and struvite and when compared to unfertilized controls. We'll quickly discuss ammonium sulfate, mostly because ammonium sulfate is a standard fertilizer and is used quite profusely, but also because this technology is novel and not much data is available on its use. Typically, when we think about ammonium sulfate, we think of it either as a liquid or a solid, and generally we recognize its nutrient analysis as 21-0-0. The ammonium sulfate that's stripped from effluent discharge, however, is only a 3-0-0 and in the liquid form. This means we needed an incredible amount of this product to get equal rates with conventional synthetic sources of N. To date, there are no reports on nutrient availability or yield responses to this product. There is no reason to think, though, that this product will behave differently than a traditionally derived ammonium sulfate. And finally, I want to mention 2 technologies that are still in the development stage. Each of these nutrient recovery technologies, vermicompost, and algal systems, are potential dairy manure users in that each technology can be tailored to use dairy manure, or any manure for that matter, as a feedstock. Unfortunately, in the Pacific Northwest, there is no available data on the nutrient product produced from either technology. However, Researchers working with vermicompost in other locales suggest that marketable yields are attainable when vermicompost is embedded to agricultural soils. Initial results from those trials indicate that application rates at 30 megagrams per hectare perform better than those at 15 megagrams per hectare, though these results were not directly compared to a traditional fertilizer treatment. Similar results in algal systems also indicate the potential for considerable nutrient recovery. These experiments, however, were conducted on a small scale, and validation of the technology and nutrient product at larger sizes are necessary to better understand its potential. Animal production facilities are often situated in agricultural regions. Advances in nutrient recovery technology, like those discussed in the companion webinar along with the products mentioned here today, are providing a real opportunity to marry the nutrient needs of a cropping system with the management of dairy manure as well as animal manures in general. That's not to suggest that challenges don't exist. Cost is a real impediment to implementing this type of approach, not to mention the variability in product that results from seasonal variation. However, as we've showcased here, there is a lot of potential. We're also involved with ongoing work to understand the attributes of these products that are most important to crop producers, with the hope that this will help drive additional technology and market development for these products. In closing, if you're interested in more detail regarding the products discussed here, do visit the CSANR library listed in the URL at the bottom of the slide. I would also like to thank those who partially funded this project: the Applied BioEnergy Research Program Internal Competitive Grant from the Agricultural Research Center at Washington State University's College of Agricultural, Human, and Natural Resource Sciences. Thank you for joining.